Okay, so welcome back to another video. So here we have a number theory problem that takes place in the 2014 Hitotsubashi University entrance exam. And we have that we want to find all triples of prime numbers a, b, and c such that a minus b minus 8 and b minus c minus 8 are both prime. So we will need to utilize the whole definition of, what makes a prime number. And so what we will do is that for the first step is that we'll actually let these be some variable such that they're also prime given with that expression, draw some conclusions and observations on utilizing, the whole definition with prime numbers and looking at some case-by-case situations on what we can do in order to help achieve what our triple numbers for the prime numbers be to satisfy are given. So really not that much to it, but I feel like this is an interesting number theory problem dealing with primes that takes place in some sort of, exam, college exam, that sort of shit. So with that, let's actually just jump right in. So I'll let the first expression a minus b minus 8, we'll let that be p equals a minus b minus 8. We'll let the second one, I'll call this one q, so q equals b minus c minus 8. Then if I were to subtract the two, and also keep in mind that p and q are primes given that the expression that these have to both be prime as well. And with this in mind, let me actually add the 8 to both sides. So that means I have p plus 8 is equal to a minus b, and then q plus 8 is equal to b minus c. Okay, and with this in mind, by definition, the prime numbers, they actually have to be greater than 0. So with this, we can actually set this inequality to say that this is actually strictly greater than 0 for both of these expressions over here. And then another thing to keep in mind is that with the difference of a minus b and then b minus c, if we actually look at this in terms of how we're given with this, we set ourselves for being greater than 0, then we can actually see what the difference is that we can come to this compound inequality to write that a is strictly greater than b, which is strictly greater than c. So with this in mind, we're now going to focus on, with the cases of even and odd numbers, which interestingly, of course, that the only even number that is a prime number is actually the number 2. So we'll be actually starting from that set from there. So with 2 being the only even prime number, we'll actually suppose that, and because that's the smallest prime number of all the, the list of primes, we'll let that be c equals 2. So we'll let c equals 2. So with that being the case, then of course that means that's the smallest number of a and b as well. Then that will also have to entail that because 2 is the only even prime number, that means a and b are odd numbers or odd prime numbers. So with that in mind, that means if we put this back together, so let me first write a and b, they're odd. So putting this back together, so a minus b, which we said that was equal to p plus 8. So a minus b, if they're odd, so if you take their differences, that means it wouldn't even matter if it's a prime number or not. But of course, a and b are prime numbers, but say if we take the difference of odd numbers, they're actually going to be always even. That means a minus b is even, also entailing that p plus 8 is also an even number. So with this being prime, and then it has to be even and even, so that means p plus 8 is even. So how do we make that an even number with that p is a prime number? Well, the smallest one, of course, for 2 is 2, and that will actually make that as a prime number. Well, if you put this together for p is equal to 2, then add that together with 8, that's equal to 10, which is indeed an even number. That's the way I should set that. So p plus 8 is even, then we can deduce and say that p is equal to 2. And so now we can come to reduce that a minus b is equal to 10, all right? And so with this in mind, now let's actually move on to the q is equal to b minus c minus h, which we said q plus 8 is equal to b minus c. Then I substitute we said c is equal to 2, so put that back in. So b minus 2, which is equal to q plus 8. I'll add that 2 back into over here, so I mean b is equal to q plus 10. Then with this in mind, I'll actually just put that back into substitution over here. So a minus q minus 10. Well, let me just add the b to both sides. I meant to put this over here, add the b to both sides. So a is equal to 10 plus b, put this here. So now we have that a is equal to q and then plus 20. So with this in mind, we'll notice that if we look at both 10 and 20, 10 is reduced to the same thing written as 3 times 3 plus 1. And then 20 is written as 3 times 6 plus 2. So utilizing with the whole division algorithm over there, what we notice is that for a, b, and q, if we actually divide, when it's divided by 3, they actually all get different remainders. This has to entail that it's either a, b, or q is a multiple of 3. And we also have that since A, B, and Q are actually prime numbers, then the smallest prime number that is a multiple of 3 is 3. Then deducing from the equation over here that we can solve for that Q is equal to 3, then just put that back in. We have that A is equal to 23 and then B is equal to 13. So we actually have our first set of triples of prime numbers. So 23, 13, and then we set that C is equal to 2, so C is equal to 2 over here. Then if we actually plug this back into over our given, so A minus B minus A, 23 minus 13, 10 minus 8 is 2. It's an even number, but it's a prime number. And if I plug in 13 minus 2, so it's 11 minus 8, 3, also a prime number, so that actually satisfied that. So that's one triple. There might be more, so let's actually solve for those. Now with this case out of the way, now let's suppose that if we let C does not equal 2, would that be the case? So that means that A, B, and C, they're odd numbers. And when you take that difference, that means that you're gonna get an even number. So that means P plus 8 and then Q plus 8 are even, which you can deduce from here that P and Q, well, I'll have to write it like this. P is equal to Q, which is actually, they're both equal to 2. So if I plug this back in, so that means I have that A minus B is equal to 10, and then I have that B minus C is equal to 10 also. Now, what I can do is, of course, let me just put that back together. So I have that A, I'll add the B to both sides from here. So that means that's equal to B plus 10. And then for this one, I'll add the C. So B is equal to C plus 10. Now with this, it's the same argument just like from what we did before. So we actually just noticed that 10 and 10, it's the same thing as over here. Now we have that A, B, and C, if they're being divided by 3, we have different remainders. Again, same thing. That means that either one of those 3, they're gonna have a multiple of 3, and we can actually deduce that. And because that A, B, and C are also prime numbers as well, we can deduce that we have that C is equal to 3, which if you just put that back into over here, then that means that B is equal to 13. This is from being smallest prime number, that's an odd number. So B is equal to 13, and then A is equal to 23. And of course, that is, again, well, our last set of triples of prime, triple prime numbers that actually satisfies the following: 23, 13, and then 3. Of course, just plugging this back in, 23 minus 13, 10 minus 8, 2, prime number. Then 13, 3 over here, so that means 10 minus 8, 2, also prime number. And so that actually satisfy yet triples, and that's the only 2 solutions that actually satisfy our given over here. Just like that, that is complete, which makes this a very interesting prime number theory problem dealing with the primes over here. So yeah, that's pretty cool if you ask me.